Right, so you have experience in optimization. So why didn't you tell me? Maybe it's all trivial what I'm saying.
I don't know if everybody here made not everybody.
Not everybody. Okay, so I'll try to find compromise. But what kind of optimization course did you have? Is it classical nonlinear optimization, or what was that?
It was linear, simplex, it was multilinear, and multi-object.
Mm-hmm. And for multi-objective optimization, what methods did you use? What? Ah, so you all know genetic algorithms? Uh-huh. Or not all? So. Okay. Well, it's a pity I didn't know it in advance. I would have then prepared something else. But let's then go quicker through this part. Right. Anyway, so I would like still to walk through quickly through steepest descent method. So, and to connect it to other methods that we'll consider afterwards. So here you see two-dimensional problem where decision variables are x1, x2, and the color shows the value of the objective function, which points that way somewhere, okay? So this trajectory here, red one, is the trajectory that you would follow if you use steepest descent method. So idea is that every time, at every point, if you start at a random point x0 here, you would calculate gradient, which is this thing, and your next point, so if this is xt, is x0, so x1 would be a point at a certain distance from x0 in the direction of the gradient. Minus shows that you have to go opposite direction because you're minimizing. So this next step would follow the gradient, this one, okay? So this would be point x1, next point. So if we look from top at this picture, you start here, you make a, so gradient points that way, or rather minus gradient. Gradient points always in the direction of increase of the function. This one points decrease of the function. So you make a certain step and stop. So this step you made here. That's first step. Question is how big is this should be this step. So if you follow this course, tell me how big is this step? Main idea. How long this step should be in the direction of minus gradient. But it's in the picture, this step. Look at this picture, it's here. Exactly. Of course. So this is direction of decrease of the function, yes, but at this point. At this point, decrease should be this one. So every step you make changes gradient, of course. So idea here is to make a step in the direction of steepest descent, but not further away than the function. So look, here function goes down, 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 down. You see this? These are isolines. If you look from top, these are isolines of this function, right? So function goes down, 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 down until this point, and then it starts growing. When you continue moving, it will reach the same value you see here, and then it will grow even further away, isn't it? You go away from the minimum. So you have to stop at least at this point, because go further has no sense. You will be going uphill, not downhill. So downhill stops here. That's the main idea of choosing the step in any iterative scheme for nonlinear optimization. At this point, what will be your direction here of the gradient? What do you think? If you calculate gradient at this point, it will point to the steepest descent, which will be this way. And interestingly, always it's perpendicular to the previous direction, if you follow this logic. So every time you will be making steps in the direction of the gradient, you have to stop at the moment when function stops decreasing and make a new step in the new direction, and every time you will be making steps at 90 degrees from the previous direction. That's the classical steepest descent method. Will it lead to the minimum? Yes, it will, and it works. Disadvantage is that you're making steps every time perpendicular, so it's not terribly efficient, but it works. With fast computers, you just use this method, and it will work. The problem is, of course, to calculate this step, because to know that function stops decreasing, you have to calculate function at every point. So it requires you to calculate function several times here as well. So in terms of efficiency, not terribly efficient, but works. So more other methods which were developed in the 70s use second derivative there and different tricks, and they would, so they're called quasi-Newton methods and conjugate gradient methods. These use second derivative, and they're more efficient because they allow you to turn earlier than you reach the moment when you turn at 90 degrees. You turn earlier at a different angle, and it's much more efficient method. So all of them are implemented in software, in often commercial software. If you want high quality, you buy packages that solve these nonlinear problems. But please understand, they all need analytical calculation of first derivative and analytical calculation of the second derivative. Do we have it in real life? No. So all these thick books written are about something which you cannot use practically for real life. Why? Because these functions are often not given analytically, and you have to use some other methods. Either you would assess derivative at each point, also possible, by finite difference scheme. So you throw points around and assess derivative more or less, and still use this method somehow updated. Or you use randomized search, as we will discuss in a second, and genetic algorithm is one of these possibilities, one of them. It's not most efficient, by the way. Right. Question is when to stop your optimization process. So this classical stopping rules. So you stop typically your iterative search for a minimum when relative difference between next step and the previous step is small. So if it's say 0.1%, then it's time to stop because you're already reached the point which is very close to minimum. So you see derivative here is very close to 0 because this is derivative assessment. Another stopping rule is when changes in x are not too large, so that you're, at the same point more or less. So difference between these two steps is small, and you also reasonable to stop. The third rule is number of iterations reaches some predefined number. So, and why this rule is useful? Because it may happen that you will be moving around and never stop. So it's useful to set up this number at a certain value, and then you would stop at this. So these are stopping rules of iterative algorithms. Okay, linear programming. If you know linear programming, then I would skip this. But in 3 words, you pose this problem in this way. So your function is linear combination of inputs, and also your constraints are linear. So simplex method allows you to, in an efficient way, to move between. Okay, let's skip this. Yes, actually, this problem was first solved by Kantarovich in 1939 when he was asked by a factory that was making planes to cut the wood because it's plywood. The wings were made of the plywood, and they wanted to optimize the cutting of the wood so that out of one sheet you would have more wings for the plane to make. At that time, planes were built of wood, some of them. So he solved that problem, and interestingly, he got Nobel Prize in 1975 in economics by recognizing his contribution to mathematics, actually, but mathematics that was used in economics. A Nobel Prize in mathematics doesn't exist. I happened to work with him in one institute, and really he's quite an interesting person. But simplex method was proposed by Danzig soon afterwards, and Danzig got no Nobel Prize, so he still perhaps feels uncomfortable because method of Kantarovich nobody uses. It was very peculiar method and for a particular problem, but it was first. See how important to be the first, even with non-efficient solution, and Danzig is sort of, and his method is used everywhere because it's, it's quite a natural way to solve this problem. So in simplex method, you move from one vertex to another in the multidimensional space, and he just proposes how to do it in a sort of regular way. Camera moved. Oh, we have two cameras now. One is for Facebook, another one is for YouTube, right? Okay, good. Okay, so I had an exercise also to solve water allocation problem using Excel, but we may skip it. Now, dynamic programming. So in dynamic programming is used, let me show this. This is CeTI-SC, by the way. So dynamic programming is one of the optimization methods which is used for stepwise decisions. So imagine you have releases which are in fact progressively planned in time, and each release leads to change in volume. So if you draw this diagram like this, you see this volume, you start with large volume, and this is zero volume of the reservoir, and this is time. So your decisions of releases correspond to different time moments for example, 52 weeks or 7 days or whatever you choose. So question is how to choose these values of releases. So every time release reduces volume in the reservoir, volume of water. So if you move this way, if you release that much, your volume drops. If you release that much, volume drops more, and so on. Of course, this is discrete formulation of the problem because releases are real values and volume as well. So in principle, dynamic programming is not is exhaustive search, but on a very limited grid. So it's a way to represent to discretize the problem into discrete values of volumes and releases, and organize the computational process in such a way that would allow you exhaustive search through all the possibilities. Exhaustive means that you check all possible releases. It's simply a nice scheme how to organize it. But in fact, you check all the possible releases out of, again, not infinite number of releases, but finite number of releases, and checking the quality function for each release. So for example, you may find out that this release would be optimal if you want to maximize certain objective function. Okay, there are some formulas. If you want to read more about dynamic programming, you perhaps had this course. It's a smart way of doing this. So Bellman, when he formulated 1957, I think it was in a way breakthrough because it allowed to apply structured optimization algorithm for important scheduling problems. And scheduling is very important for economics. You want to schedule certain deliveries, you want to schedule releases, and so on. So that was an important contribution. One of the most important contributions to the theory of optimization is development of dynamic programming, actually, as long as simplex method for linear problems. Okay, but please note, this problem, this method is applied for single objective. Okay, you find the releases which would minimize or maximize your single objective, for example, electrical power generation. So it's not multi-objective method. But it's still widely used in hydropower and as a possible tool to optimize the releases. Okay, let's... Right. So now let's think. Yes, yes. Sure, sure. You also have to teach. Yes. Yes. Okay, thank you. So advantages of the methods that would use derivatives is considerable because it allows you to organize the computational process in a structured and fast way. So for not very complex problems, derivative-based methods lead to a solution quite fast. So computationally, they're very efficient. The problem is, as I said, we often don't know functions analytically. For example, when we talk about humans that consume water in water distribution systems, what is then the, how do you measure this level of satisfaction or difference between supplied water and what is needed at different households? Can it be written down analytically? Question to you. Can you write a formula for this objective function? Yes, you can? You can write a formula. Interesting. What would be this formula? So, for example, you want to ensure that at certain household, the pressure head, at that point, is not below a certain level. So what is the formula for the head at that point? You said you can write it? Well, look, this value is given by a model. You have to run EPANET model or any other model that would calculate head given all other factors that influence the water distribution system. So there is no analytical function for many of the things. You cannot write it analytically because there would be some variable which is given to you from some models, or maybe many variables, or the whole thing is the result of model run. If it's the result of model run, how do we find derivative of a function that is calculated at one point only? You cannot. You can assess it, yes, but analytically you cannot do it. So that's why the set of methods for optimization, which is based on calculated function at one point, is very different from what we use in classical nonlinear or linear optimization for that matter. By the way, about linear, most problems in life are not linear. So this method can be used as a first approximation when you cannot do much more, but in fact, it's a bit useless nowadays because most problems are very well understood and they're not linear. Nothing is linear, practically nothing. Most processes go slowly up, then develop, and then slow down. Or some processes go up and then down. It's nothing to do with linear functions. Practically nothing can be described as linear functions. So this is a nice exercise and to understand how it works in general for linear cases, but often it cannot be used. So returning back to our optimization. This is classical case when you have single extremum, single minimum. That was strong assumption when we discussed this. We assume that if we start search at some random point and we'll be moving towards the minimum, we'll reach the minimum. And often this is the case, but what to do in this case? So some functions are multi-extremum. It means they have many local minima. So at this point, derivative is 0 and gradient is 0, but this one is not global minimum. This is the only global minimum in this function, and these are all called local minima. Okay? So to find local minima is also nice, but it's not the optimal solution, because this one is the solution, not this one, and they're quite different. And if you plot various functions in real life, you will see they have multiple extrema. So they're called multi-extremum problems. Extremum stands for minimum or maximum, it's the same thing. And how to solve this? Even if you have analytical description of this, and you use iterative scheme to solve it, you start somewhere here. Imagine this is your random point. You move along the gradient to this point and you stop. So can you propose an update to this algorithm that would allow still to at least to have a hope to find minimum, global minimum of this. Exactly. It's called multi-start. So we would start at multiple points, the same process that we described before. So if you start here, you arrive to this one. And if randomly you start here, you arrive to this one. But if you're lucky to start here, you arrive to global minimum here. So multi-start is used, so you randomly generate x zeros, initial points, and you start parallel, independently, search for a minimum. You can also parallelize this process, which is nice, to multiple computers, and in the end, you hope to arrive here. But if you are not lucky, if your points are not in this range, but somewhere else, you will never arrive here. Uncertainty in life. So these methods are called direct search methods when you don't have analytical description, or often we use a randomized search. So now let's look at this. Process of calibration of a problem. Yes. Let me see. Yeah. So maybe we'll do it after we discuss this. So let's return back to this in a second. Just want to say that optimization problem of calibration cannot be solved analytically. Why? Because the model generates output, and error indeed is a formula, which is root mean squared error, nice formula. But in that formula, you have output modeled, which is given by model run. And there is no derivative here. You cannot do it. So that's why even for simple problem of model calibration, you have to use random search methods or direct search methods. So let's skip it because I want to show you how software does it for our wonderful tank model. So if we summarize the approaches to solve optimization problem, then if f is a single extremum function expressed analytically, okay, even if it's constrained optimization, which is called non-linear optimization traditionally in books, you use some of these methods which are implemented already in software. One is called Levenberg-Marquardt method, which is widely used, and set of methods which is called conjugate gradient methods, which are efficient, very well developed, reasonably reliable, and you can just pick up the software code, or you implement it yourself using, for example, the book called Numerical Recipes. Have you heard about this book? Numerical Recipes, so highly recommended. Some older versions are freely downloadable also. And code is written in C, Fortran, and Pascal, and maybe something else also. So widely used book. But the codes which are in this book are not necessarily reliable, be careful, because for complex problems they may go God knows where, so be careful. So if you want really to solve complex problem, you better get commercial packages, which are tested for years and years by different applications, and they're bug-free, so to say. But they cost some money. So second example is when f of x is single extremum function. It means we assume single minimum, but it is not analytically expressed. Okay? For this thing, we can use set of methods which do it, and they are developed, as you can see, long ago and still can be used. And in numerical recipes, you have implementation, for example, in downhill simplex method. Do you know about this method? Not simplex method, but downhill simplex. It's a different thing. It is not linear programming method. You also used it, Nelder and Mead? Yes. Yeah, you used it? Ah, that's great. You remember this, everybody? So it's not for linear problems. It's not simplex method. It's just, unfortunately, they have chosen the wrong. Okay, we'll look at it. Let's discuss. And then the third option, which is typically is present in water problems, is when you don't know much about this function f. You can calculate function f at any given point, yes, but you don't know if it's convex, whatever. You cannot calculate derivatives. You don't know how many minima it has, nothing. And then you would use randomized search methods like genetic algorithms. And also these methods are called multi-extremum or global optimization methods. So it's more or less the same, but global means that we do not assume single minimum, but want to find global minimum. So we may assume many local minima, but we aim at global. That's why it's called global optimization. There is Journal of Global Optimization and so on. So that's an example of one of the benchmark functions that is widely used. So you can see this is the formula over here, not terribly complex. So it's analytical and it has two minima. So it's widely used for smooth function for testing different algorithms in optimization. Okay, yet another example. So main approaches to direct search. Space covering techniques, which cover space with points, and then we do something about this. Random search methods like evolutionary and genetic algorithms. Multi-start, where we start at different points and then we use different algorithms and we could combine them. So that's also a set of methods developed in the last 15 years maybe. And other methods, simulated annealing, tunneling approach, ant colony optimization, bees flying, birds flying, and all this stuff. It's all randomized search methods. Just people invent nice names to sell them well. So there's a website where they listed, I should find that website, where they listed all these funny names for all these random search methods. They say these points are ants crawling, or bees, or birds, or whatever. But it's purely random points. From the point of view of mathematics, it's just random search. But okay, we'll look at this. So random search. So what do we do in random search? Let me start here. Pure random search. x1, x2 are independent variables. Objective function points at you. You want to find minimum. What do we do? Very simple. We generate randomly, uniformly, from uniform distribution, values of x1, values of x2. We form the vector out of these two random values. We put a point here, and we calculate function at that point. So in this case, how many points here? I don't know, 100 points. You calculate 100 function value 100 times. So if you have to run the model, you have to run the model 100 times. If one model run is 1 minute, it's 100 minutes, don't forget. But you can parallelize. So if you use cloud computing, you can run 100 computers and then get all the results. So it will be much faster, of course. And then you find the x1, x2, for which this function is minimum, and that's your minimum. That's it, done. Pure random search. Pure because we use uniform distributions here and here. We don't know much about function properties, so we cannot do to judge anything. We just do pure. It's a first guess. First guess. Useful to do, actually, before you do anything. And you can plot it also. Maybe you could somehow plot it in multidimensional spaces. Difficult, but possible. Now, genetic algorithms. So terminology was borrowed from natural solutions. So these ideas of using what happens in nature started to appear in the 50s and 60s, but then different people formulated differently. So in the end, there were two schools formed. One is called genetic algorithms, another is called evolutionary algorithms, which is more or less the same. So we call all points population, so there is a species which develops somehow, and each point vector x1, xn. So these are independent variables, which is called chromosome, fine. And chromosomes are made of genes, so each variable coordinate is a gene, okay? So it sort of replicates what's happening in the nature when species mate, and then they generate new species, and they pass forward some of the genes from parents to children, and this is how evolution goes. And evolution says that species which do not fit environment would die, unfortunately, what can we do? And other species would survive, which are fit, and they would continue and continue. So that's main idea borrowed from nature. So there are many positive things about genetic algorithms, but I would like to point also to some strange things which I thought would be useful to mention, because in the books of genetic algorithm, they're not mentioned. They just promote this as a main idea. It solves everything, everything genetic and all this stuff. Even I remember I wanted to submit a paper, it was in 97, I think, about algorithm I developed to one of these evolutionary genetic conference, Gecko, I think it was. But then I read in the what papers I accepted. So papers, it was written papers I accepted, those papers which show the advantages of genetic algorithms above anything else. It's a scientific conference. So it was a bit funny. It's the first time I saw it, not before, nor later. So that was funny phrase. Maybe it later disappeared. But it's sort of a community of people that talk to each other and award each other medals for great achievements. But of course, there are other people who invent alternative methods, also build schools and optimization, whatever. So and they talk to each other and say, "Ooh, we're faster." So it's interesting to have competition. It's always good. So those of you who never did genetic algorithms, still I have to spend 5 minutes on this. It's part of the lecture, and maybe it will remind you, but I would point to you and ask questions. What do you find strange in the genetic algorithms? And why do they work and why they may not work? That's important. So consider we have two-dimensional space, two decision variables, okay, x1, x2. Function points at u, and we can calculate function value at any point. Imagine we start with the population of 2 points, 2 parents, so parent S, parent T. So in two-dimensional space, what standard canonical genetic algorithm says that we take coordinate. So you see these are genes forming the chromosome here, gene 1, gene 2. But in fact, these are simply real values, x1, x2. So we take parent S and form and parent T, so this is present, and now we're forming new points. We generate new vectors in vector space of decision variables. Offspring 1 would inherit x1 from parent S and x2 from parent T. And this will be new offspring. This offspring would inherit vice versa x2 from parent S and x1 from parent 2, and it will be located here. Now we have 4 species, right? 4 chromosomes. So we had values calculated for parents already. Now we calculate values for offspring. So it's 2 more function evaluations. We have 4 in total. And then what we do, we choose 2 best. Okay? It could be parents, it could be offspring. Or in other things, we kill parents and we leave only offspring. Also different versions. But mainly we generate, so if you have n parents, you randomly mate 2 parents together, you form offspring like this, and out of 2 endpoints, you select n best points. So in 4-dimensional case, this would look like this. So if this is values of independent variables for 2 parents, offspring would be generated by random choice of cut line here. So from here or here or here, we cut this, and first offspring would inherit blue from the first one and red for the second, from the second parent, and second offspring would inherit x1 from the second parent and blue from the first parent. Okay? Now tell me, think about this. So why genetic algorithm people think that this offspring would be better? Because the main idea of generating offspring is to generate better points. Better, what does it mean better? With the lower function value or higher fit. If you maximize function. If you minimize, you minimize. So better. Better means lower function value if we solve minimization problem. So why do you think these 2 offspring have a potential to be better than parents? That's what I said 25 years ago when I first learned about this problem. I thought, it's a bit strange idea, actually. So they say it's happening in nature like this. But nature is very inefficient. Nature generates many more species like this than needed in order to ensure reliable reproduction. But when we design algorithms, we want to be very efficient because we don't need redundancies. Because redundancy means long computer time, and we don't like it. So it shows, actually, in fact, since you cannot see the reason why this would be better, and I don't see it immediately, I think it's pure random generation of new points by a recombination of these things. Like on this picture, look, you may endlessly move. If these are good and these are bad, you would kill offspring, bad offspring, you leave good parents, they will again mate, generate bad offspring, you kill them, and it would be infinitely long search, leading to nowhere. So it may happen also in multidimensional spaces. When you generate offspring which are not good, you kill them, you're again left with these parents. However, this choice of cut may be random, and then you generate new offspring, which some of them could be worse than they're killed, but if they're better, they're left. Then you remove bad parent, you leave good offspring, and you improve quality of the whole population a bit on average. So main idea in this genetic algorithm is this. You take population of n points, you generate n more points, like using this method, okay? And then you merge them into 2n points. N could be 100, for example, often 100, 200. So if it's 100 here, you randomly mate parents, you generate 100 more offspring, so you have 200 points in total, and you remove 100 of bad points. So look, if you have a population where you remove bad points, you immediately, not immediately, but high probability that you will have a better population with, on average, lower values of function value. So imagine, and this is good. So this is a random generation of points, and then removal of bad points, and you are left only with the better points. So you gradually would move towards the minimum. Since average quality of population improves, you would move towards the minimum. So imagine this is two-dimensional space and function points upwards. So guys, you are all, no, I'm not saying you have to mate now, but imagine you are parents and you generate offspring. So don't do it now, maybe later, but not now. And now I remove bad guys and good guys would stay, exactly the same number. So they would move slightly towards the minimum, isn't it? Because their function value is lower, so the whole thing would move. Imagine minimum is somewhere here. So this whole population, which started somewhere randomly across the room, would move a bit towards the minimum on average, because on average it's better. Then we mate again, generate new offspring. It would again improve a bit and move a bit towards the minimum. And it will be, in a way, following the gradient, isn't it? But assessment of the gradient, implicitly, it's not explicit here, but it's implicit. Because every time all these points would improve and they would all, as a crowd, would move towards the minimum. Every time you will generate many new points, yes, randomly, but they will be killed. What may happen that if it's a minimum, but imagine you have another minimum there, and you don't know about this. Randomly, if you generate good points there, they will be left because they're good. And in this way, you will discover second minimum, or maybe more minima. And you will be gradually, by random search, moving towards this local minima, and in the end, you will arrive to them and stop, and then choose the global minimum. So that's the whole idea of random search. Randomly generate points, remove bad points, leave good points, and your population would gradually improve. Why genetic works better? It has been shown, no, it doesn't, because there are better schemes of choosing this offspring, which are more efficient than canonical genetic algorithm. Why still it's used? Tradition, implemented software, authority of the people who wrote books at the right time, like Goldberg and others. And why not? They contributed to optimization considerably. They didn't care much about efficiency, but they made an enormous help towards the people to use at least some of the algorithms, and it sells well also. Genetic, it was a New York Times, you know, we use laws of nature to find optimum, Christ's sake, all this nonsense, you know. What laws of nature? This is law of nature? No. Okay. So it's very far from this. But it's nice. If you want to sell your idea, you wrap it up in a, you know, in a nice story. And this is what's happening with genetic algorithms. Then you want a new nice story. You say, oh, no, it's not, it's ants crawling, you know. Ants are very smart. They exchange information. So maybe these guys would exchange information, and every time ant moves to a better place, it would send a signal, you know, chemical signal to other ants, and other ants also move to it, and all these ants would move towards the minimum. Or birds, flock of birds, you know, there's flock of birds algorithm. Birds fly to the food, and they search for food, and there is a smell from food, and all these stories, you know. That's great fun. So why not? If you have fun with science, why not to do it? Especially when it works. And most algorithms work because it's random search. Why not? It just sometimes spend more computer time than you would expect. But why not? Now, in genetic algorithm, often we encode real values by binary to sort of make even closer picture of a chromosome, which is, you know, binary codes, you know, 1 of 4 codes, like DNA is encoded, and then you form the chromosome as a sequence of bits like this, because look, this is 5, so it's 1 plus nothing plus 4, it's 5, right? This is 20, so it's 1, 2, 4 plus 16, 20, 9, so it's 1 plus 8, 9. So all these digitals are digital values, decimal values are encoded as binary. You form a binary string, like in genetic algorithms. Did you do it? Binary strings? Oh, you forgot? Sorry? You do what? Right. Okay, I understand. But so that's what's happening in a lot of software. It's encoded as bits, and then you may cut not only between genes, but also in the middle. And then this thing take place like this, and cutting in the middle and then changing this place is pure random thing. Because there is nothing good you inherit from this gene when you put this, it's pure random. So it's a pure random jump in the direction of X3. That's what's happening. So all of it is, in fact, very close to just normal, like here, you see? You had this, and then you would have a new number, completely different number. So it's pure random search. Right, so that was genetic algorithm. Okay, there is some description of pure algorithm if you want to implement it yourself. Yes, there is also a German school of evolutionary algorithms. And they were in fight with American school a long time, and then they somehow became friends, so I'm not sure what happened. And then at one of the conferences, it was maybe 15 years ago, they said, now we call evolutionary and genetic algorithms in one go, EGA. Okay, it's not followed actually. Typically we say either evolutionary computing or genetic algorithm. So German school made a smart move. They said that when we recombine these chromosomes, we do this. Look, this is 2 parents, S and T, same thing as before, 2 parents. Now we had the pen, right? So what happens with these 2 parents? So if this is x1, x2, x1, x2, objective function points at u, and so this is 1 parent, so this is S, this is T, and now we generate an offspring. So this offspring is the same as previous parent, S, but move to the direction of T. So in fact, this S dash is somewhere here, because we connect 2 vectors T and S, find the difference between them, and recalculate coordinates of Si into Si dash. And this Si dash is here. This is what German school does in their evolutionary algorithms. And that's a smart thing. So look, if this is good and this is good, we may find even better one halfway through. So mu could be move here or here depending on mu. If mu is 0.5, then this is this. So if this is good, so maybe we have this situation. If this is objective function and this is x, maybe this is s and this is t, and maybe function goes like this. So if this is like this, maybe we find a better value between two good values, right? So that's an idea, actually. And it works. So it was shown that this method of recombination leads faster to the minimum, okay? That's the German school. And actually, if you think about this, it's very close to gradient search. You think of low values, and then you make a step towards the low value. From this one low, you make a step towards another low, and you hope to find somewhere here. So that's a bit of analogy with gradient search. Excellent. Thank you for reminding me. So we're 7 minutes late. So the break, shall I suggest, ends at 10:35? Good? Thank you.